Hello, welcome to Computation in C. My name is Josh Kilpatrick. I am a retired software engineer, and this course is designed for beginners who want to form a foundation in understanding computers, programming, and more generally the science of computation. We're learning the C language together, and we're going over the history of computing. Today, I am really wanting to focus on the very beginning, sort of mankind's history with mechanical computation. So let me ask you, or let me share with you something that you may not know. The first use of the word computer was used to refer to a job that a human had. These were often females, and here we see a picture of an office full of women who worked at NASA, around the 1930s, 1940s, before we really had the use of modern computers. And a lot of the maths and sciences that needed to be done required a lot of just computing numbers, multiplying numbers, evaluating equations. And these things were done on paper with the help sometimes of mechanical machines. You see some of these mechanical machines the women are using there to help reduce errors and to help the people add the numbers, multiply the numbers, subtract the numbers. This was a job called being a computer. So I want to step back and really look at the history, human history, and what we've been doing as humans that has sort of led us into the age of modern computing. And I think this is a really neat story, a little bit of math review in this lesson, and kind of laying the foundation for our next video, which will be getting into the early modern era of computing. So today we're looking at the really, really old era of computing, up until the 1800s. So let me start here with a timeline. Now, the earliest devices that we have from archaeology that demonstrate that human societies were using mechanisms, mechanical mechanisms, to help with math or to help with counting dates back to China. This is 1,000 years before the Common Era. We have found evidence of these devices called abacus and abacus. And I'll show you a quick photo of an abacus here. Oops. Thought I was going to show you a quick photo of an abacus. There we are. These are generally some sort of square device with beads on sticks, and you move the beads on the sticks to sort of count numbers. And these were organized in a system where each stick represented a power of 10, and you would count by sliding the beads 1, 2, 3, 4, 5, and then you would slide the top bead up to indicate you would hit 5, and you would get 5, 6, 7, 8, 9, 10, and then this top bead represented, the top beads right here represented 5s, and the bottom beads represented single numbers. So you would count 1, 2, 3, 4, 5 by sliding these beads up, and then once you hit the number 5, in order to get to 6, you would push all the beads back down. You would move one of the top beads up, indicating, I've hit 5, and then you'd slide one of the bottom beads up to add 1 to 5, and you'd get 6. And as you went through the different columns of the sticks, it was like going through the different places of a numeric system, the tens place, the hundreds place, the thousands place, and you could sort of count numbers. And this was useful because, you don't want to have to remember where you're at in counting, or sometimes maybe sheep are coming by and you're wanting to count how many sheep are coming through the gate. you can imagine uses in the ancient world where people needed to understand how to keep track of numbers and how to count. So we have the abacus showing up really, really early in human history. I'm going to jump way ahead now, past the abacus. I don't think a lot of interesting stuff was recorded after the abacus. But something really interesting starts to happen right around 1614. Now, we've entered now the age of enlightenment, where maths and sciences and sort of a love of reasoning and the scientific process are really beginning to take off, kind of putting the Dark Ages behind us. And a famous Scottish mathematician, John Napier, invented logarithms. Now, you might have heard about logarithms as something that you learned in maths class, and they end up being very important as we move into the age of computing as sort of a stepping stone. And I'm going to show you here in some examples what John Napier devised and how modern, or they're not really modern, but Enlightenment era and beyond scientists really managed complex math. So let's start with this logarithm process, and I'll show you how this worked. So let's get started first with something really simple that we all have heard of and know how to do very easily. Say you just had two numbers that were fractional numbers, so you have decimal places here, and you wanted to add them. We've all learned how to do that. It's pretty easy. 7 plus 4 is 11. I'm going to put a 1 down and carry a 1. 5 and 2 is 7. With my carried 1 gives me 8. 5 and 8 is 13. 3, I'm going to carry a 1. 4 and 1 is 5, plus 1 is 6. So 63.81 is the sum of these two decimal numbers. Probably could have done that in my head. It's a pretty simple operation that didn't pose a lot of challenges to humans. However, if, as we get to some of the more complex maths, we want to perform a multiplication of two 4-digit numbers, and this is a pretty modest numerical problem. Imagine if there were 8, 9, 10 digits here to these numbers, how much more complicated it would get. But I'm sure you remember from grammar school, you have to create the multiplications of each of these places and then sum everything up. So it would look like this. 15.27 times 4 is going to give you 6108. And then you have to do the multiplication again by 5 by moving over a place and adding a 0, and you'd get 7635. Then you have to do the multiplication by 8, and you'd move over to the hundredths place, or to the tens place in this case, and multiply the number out, and you get another big number. Finally, you'd multiply the 4 times 15.27, and you'd get this number. Then you'd add them all up, and you'd end up with 741.2058. I'm not going to obviously go through the mechanics of the multiplication process, but I've just sort of tried to walk you through, okay, that takes a minute or two to work that out and come up with the answer. So what if you were having to do lots of these multiplications with lots of different larger numbers? Number one, it takes time. Number two, it's error prone. So in the 1600s, John Napier comes along and discovers logarithms and the properties of logarithms. So let me give you a quick refresher on what a logarithm is. A logarithm is basically to take the logarithm of a number, specifically the base 10 logarithm. We're asking, to what value do I need to raise the number 10? To what value do I need to raise the number 10 in order to get the number that I'm trying to take the logarithm of? So this is sort of like a reverse exponent. We're saying, hey, if I want to take the log of a number, I need to know what number do I need to raise it to in order to get 10. So to give you a simple example, the log of 100 is 2. Because if I raise 10 to the power of 2, that's 10 times 10, 100. So that's the log of 100. So hopefully this is just a refresher and you've heard of logarithms. So how were logarithms actually getting used to speed up mathematics? Well, I'm going to show you a little sort of magical math to help you reason about this. So if I wanted to say 10 times 100, we all know in our brains this is pretty easy. I just add a 0 and the number is 1,000. But another way to think about this would be I could represent 10 as 10 to the power of 1. I could represent 100 as 10 to the power of 2. And I would notice that the answer of 10 times 100 is 1,000. That's 10 to the power of 3. So what pattern do we notice? Well, if I add together these exponents, I get the answer. So if I want to multiply two numbers, if I can represent those numbers as a power of 10, if I just add together the two exponents, I get the answer of the multiplication. And doing addition is a lot easier and a lot less error prone. So Napier comes along and kind of discovers and documents these properties, that if we know the log of two numbers, the sum of the logs is the log of the product of the two numbers. So let's do a quick example here where I'm going to walk you through how this process would have worked, and then I'm going to explain a little more about how early professional computers were using these logarithms. So let's take our two numbers, 15.27 and 48.54. So the first thing I have to do to use logarithms to perform a multiplication is I have to take the log of each number. So what is the log of 15.27? Well, to make this super easy for us here, I'm just going to pull open this scientific calculator on Google and enter in 15.27 and take the log of that. Oops, I obviously didn't use this calculator correctly. 1 second. I'm going to take the log of 15.27 and say it equals 1.183. So just to summarize here in my example, I'm just going to write down 1.183. Okay, now I'm going to take the log of 48.54. Let's see what that looks like. So I'm going to clear out this number and take the log of 48.54. And I'm going to end up with 1.686. All right, let's record 1.686. Okay, 1.686. Now, by the algebraic laws that I was just showing you, I can come up with the product of these two numbers by simply adding together these logs. And so I get 2.869. And now my question is, okay, 2.869 is the log of the answer. It's the log of the product. So in order to figure out what that number actually is, I just raise 10 to that power. And when I raise 10 to 2.869, which we can do with a calculator, we get the number 739.6. Now, if you remember back, you might say, well, gosh, Josh, that's not exactly the number we got when we multiplied. And you're right. The reason is because I estimated the logarithms here only to 3 digits, and I didn't really do the rounding in a very reasonable way. So my answer is a little off, but you get the idea that 7.39.6 is, it's in the ballpark of 741. Now, if I had extended the logarithms to more places of significance and or rounded them more correctly, I would have come up with something very, very close to the actual answer. Or exactly the answer if I had done it to enough digits. So through this mechanical process of looking up logarithms, I can avoid doing this long mathematical process, which is very error prone. So let me show you an example of what people were actually using to do these processes. This is a page, an excerpt out of a really old logarithm book, one of John Napier's books, and you can see here there were tables of numbers that represented the logarithms of all the known numbers up to a certain number of digits. And so in this book, you could look up in a table, that's a picture of John Napier, you could look up in a table what the logarithm was, add the two numbers together, and then there would be another table to do the reverse lookup and ask the question, hey, of what number is this the logarithm? What is 10 raised to this power? And you would be able to, just by doing a few lookups and some tables and some additions, you could come up with the answer to a pretty complex multiplication. You could do the same thing in another form for division, making multiplication and division much less error-prone and much more systematic. And this was the advancement that was introduced by John Napier. And this is something that's really going to lay the foundation for a lot of the future of computing and advancements in doing maths and sciences. So let's come back now to... We had John Napier in 1614. He created these logarithms. And by 1632, we have the first mechanical slide rule. If you've never seen one of these devices, they look kind of like this. And a slide rule was a mechanical instrument that you could use to perform additions and subtractions, divisions and multiplications, using the concepts of logarithms without having to go look things up in tables. It was a mechanical device. It was based on the principles of logarithms, and you could multiply and divide different numbers using a mechanism. Something much like these were used by early engineers before the invention of calculators in the 70s. So slide rules were a popular technique for doing mathematics. So along in the next stage of our timeline, if you kind of position yourself in history, right after these advancements in mathematics and the Enlightenment, right around the mid-1700s, what we call the modern industrial revolution begins. And what do we get? We get the engine being invented, and a lot of new advancements start to happen in society. Trains and more sophisticated problems that people were beginning to solve as they moved into the Industrial Revolution. And right around 1812, so, roughly 75 years into the Industrial Revolution, as we said, maths and this process of using logarithms was a very important computational tool. A guy named Charles Babbage wrote a bunch of papers for an invention that he called the difference engine. And this was the first real good example of a mechanical computer. It looked something like this, that had a bunch of gears and dials, and if you operated it correctly and turned the crank, you could add, subtract, multiply, and divide complicated numbers using a very similar system as Napier's system, using these sort of logarithmic approaches. And I think that it's really amazing to realize that, long before we had computers, men and women were already thinking about how can I create a device, a machine that will simplify these computations that I'm having to do. So that gets us up to 1812. Charles Babbage and his difference engine. So what happens in the next years? I just want to kind of situate you in history. So by 1831, Michael Faraday had invented the dynamo, which allowed the production of electricity. The electrification of North America and the world began. It was 1843, not long after we had electricity, someone invented the telegraph, and we began to be able to communicate across long distances for the first time in human history. By 1877, the telephone was becoming commercialized. It had actually been invented or envisioned a bit earlier, but by 1877, Alexander Graham Bell is founding his Bell Telephone Company, and the telephone is starting to move around the world, allowing voice communication over long distances. And then finally, right at the beginning of the 20th century, air flight occurs. We discover how to build a plane and how to move humans through the air. So what I'm trying to position here is, right up until the early 20th century, we had been doing a lot of manual computation using these logarithm tables to evaluate very complex physical systems and organize different mathematical problems to solve real-world issues. And in the 19th century, we really see an explosion of new technologies that are going to require a lot of maths and sciences to understand and to unleash the potential of. So the invention of electricity, the invention of the telegraph, the invention of the telephone, and the invention of flight, or the discovery of how flight worked, now become the catalyst for a whole new slew of new engineering problems that require more and more and more maths. And we're going to see in our next video kind of what the next step in the chain is. Now that we sort of have all of these problems, we're applying math to solve so many valuable engineering challenges in the world, and we're wondering, gosh, how can we do more math faster? So we don't have to do math with a room full of human computers. We can start to do it mechanically. How can we take this vision that Charles Babbage had with the difference engine and come up with something a little more practical, a little more functional, that will really start solving some of these math problems? So here we are at the beginning of the 20th century. We're heading into the century where the modern computer age is going to begin. And in our next video, we're going to pick up the tale with something that began to happen around the 1930s with a very famous mathematician who really invented the concept of how we think about computers today. His name was Alan Turing. And we'll start with him in the next video and bring ourselves up to date on how the modern computer really started to be envisioned. Thanks for being here. I hope to see you in the next video.